everybody. Welcome back to another whatever this is that we do twice a week on this channel. Live stream, I guess. My name is Tony. My name is Tunya Darnell. I'm from Deep Astronomy. I run this dumpster fire that we call a hangout. And today I want to talk about black holes because everybody loves black holes. We cannot get enough of talking about black holes. So today I'm going to talk to you about some of them because there's a lot more kinds of black holes than I think we can fully appreciate. So I'm going to look at some of them today because, wow, we've learned a lot about the universe since the 1700s when Pierre Laplace, first theorized them. He's a French mathematician who first said, you know what, black holes might be a thing. And then along came Albert Einstein, our old friend, and found out that, in fact, that is true. So we're going to talk about them today. But first, I wanted, let me just let you, I'm sorry, I'm getting distracted by the chat here. So I'm chatting YouTube, Twitter, Twitch, and YouTube, Twitter, Facebook, and Odyssey. Odyssey is the platform that I'm really interested in these days because that's a blockchain-based thing that lets me own my content. And much like the NFTs, I get to at least prove that I created this content because NFTs are useful. Okay, so anyway, I'm monitoring all the chats from everybody so we can have questions and comments. I'm also this time, and I haven't been doing it lately, but if you join the Discord server, the link's in the description box here below. I'm going to go into the voice channel here in a little bit, and we can talk if anybody's there. I've been neglected to do that the last couple times because I forgot about it. So we're going to try that also this this time around. Please let me know if you can hear me okay. Hopefully, I'm going to look at the chat here. Let's see. Oh, look, we can buy followers, primes, and viewers on this thing, ... So let's do that, shall we? Because gosh knows our community / cult needs all the help it can get. You know, I haven't been fair about this, to be honest. I realize, you know, how I'm always talking about community and how we build our community, but it really is more of a euphemism for a cult. Well, I'm not telling you the whole story because I got to thinking about this, and it seems to be a little bit deeper of a topic than what we would initially think. Sure, cults develop into these online platforms, but really what we are, what has brought us all together here today is really that we kind of all click on the same links. You guys happen to click on the same links that I click on. So we're all in the same algorithm together. That's what has initially drawn us together. Now, once we all click on the same links and the algorithms bring us all together, it's my job to say things interesting enough to you that you will want to join my cult. And that's the trick, right? That's the part that, you know, I have to, that's the heavy lifting on this whole thing. So really, all of us share the same interest in the same links on the internet. That's who we really are. That's our real connection to each other as I see it. What do you guys think? Okay. So I know I go on about this because I just wonder about what we're all becoming in this day with all of this technology that's supposed to bring us together but really doesn't, and what it really does to us. There's a lot of philosophy that goes into this, and I've become a more philosophical person as I've gotten older, as you know. Greetings, everyone. So thank you. It's good to see you guys. So loud and clear. That's good. John, it's good to see you. Welcome back from the UK. You're in the central part of the UK, if I recall. I don't want to give away your location because I don't want stalkers to come get you. But I think you're sort of. But anyway, welcome. I'll just say UK. Peter's also in the UK. I won't say where. Although if he ever talks, you'll know immediately where he comes from. Jordy. So anyway, so let's see. I'm just going through some of these. Evening, Dennis on Twitch. It's good to see you. So here we all go. Soul, oh, you're in the West Mids of UK also. Well, welcome, Soul Soprano. It's good to have you here. A lot of UK, Yorkshire. I love Yorkshire. I want to go to York because there's a lot of Viking stuff there, and I love that stuff. So I want to go see a lot of Viking. I haven't gone yet, but I hope to. My wife's a Geordie, so I go up to England every chance I get. We go and visit family and stuff in the Northeast. A little bit chilly right now where you are. Raj, I know you're in London. I know, Raj. I don't forget about you. How can I forget about you? You're here, and you're always a good member of our cult. So thank you. I appreciate it. Norway is another place I'm dying to get to. All and check out some of the scenery there. Peter, you just posted a link on Discord that is going to be the topic of a future stream where you're talking about how Boca Chica, that's the SpaceX launch site in Texas, is actually causing a lot of environmental havoc down there with wildlife. That's something that means a lot to me, and I'm going to do a stream in the future, although I'm still putting together the research on it, about the environmental effects of all of these launches. How many, what's the carbon load on all these launches that we're doing, as well as the environmental effects. Now, say what you will about NASA, and we all say everything about NASA, whether it's good or bad. One thing I'm very proud of here where I live in Merritt Island, near Merritt Island, which is where Cape Canaveral is there's a wildlife refuge there that we just went to last week, Charlotte and I. We drove through this drive that you can go through through the wildlife refuge itself. Absolutely stunning. This is the time of year to do it because a lot of the birds are down there and stuff. NASA has done a great job of keeping that area pristine. And so I'm very proud of the work that NASA has done environmentally anyway, with that. But I want to talk about that later. And I know that you brought this up in Discord. I'm going to read that article. I think I've read that article actually. So there we go. So welcome, guys. I've got your. I'm gonna not look at the chat for a while because, as you guys know, I tend to get distracted the minute I forget what I'm going to say. And if I ever do this where I'm talking and then it means I've lost my train of thought. So I need to concentrate. I'm looking at this camera and I'm going to look at my notes to talk about black holes here. So I want to pull all this stuff up. Let me start. I don't have a whole lot of graphics, but I am going to put this up. Oh, where did my, oh my goodness. Why is Charlotte texting me now when she knows I'm streaming? Okay. There. That's what I wanted to show. That is a black hole. It is the only black hole we have directly imaged. And I get made fun of this a lot by commenters on YouTube a lot because, well, they're YouTube commenters. But I made way back in 2009 when I made my journey into a black hole video, I made the statement, black holes are actually simple objects. And they are. Black holes are actually quite simple. They are characterized. They're characterized by three main things, really. Their mass, whether or not they spin, and whether or not they have a charge. Now, their mass, if you just have a massive object that was sitting there, that's called a Schwarzschild black hole. Just a basic one each black hole. Now, I'll talk a little bit more about these different kinds here in just a minute. But I want to let you know how they're characterized. And black holes can spin. And if they do spin, then they're called a Kerr black hole. And that's just a Schwarzschild black hole that spins. Now, when they do spin, they create a torus-shaped event or a gravitational field around them that, the warping is so intense that the light can actually warp all the way around the black hole itself. And that's because of the spin of the black hole. Most black holes in the universe are probably this type, Kerr black holes. And they can possess a charge. As things fall into a black hole, protons, electrons, whatever the charge may be, can build up and they can become charged. but it's usually negligible, and a lot of calculations don't usually include charge as one of the major defining characteristics, although it is a property. I'm not going to go into these theoretical things right now about hair and no hair. That's a topic for another black hole stream. But because this one I've got a lot to go into even without touching on that. But that's a theoretical Hawking uh, radiation kind of theory about hair on black holes, and that's I don't want to talk about that right now because that's a lot. So, but I feel like I needed to have a disclaimer here. And I hate to say this in this day and age because, well, a lot of people, are drinking bleach and doing all kinds of weird things to cure themselves from a virus. So I feel like I need to say this. If you fall into a black hole, you will die. That's what everybody says this, all the astronomers. So don't go falling into a black hole because you will die. You won't come out the other end in some kind of white hole in another space and time kind of situation. That's not it. You're going to die. If you go into a black hole, that's it. So dangerous places. Not that it's really something we've got to worry about all that much, but it's still something I feel like I should say in this day and age, just to kind of keep us all, to keep me from being sued. Okay, so when I started this, and I've been communicating science for a while, I've been looking and I've been interested in black holes for a very long time. When I first started this, it was actually a pretty simple it was a pretty simple area of study. There weren't a whole lot of different kinds of black holes. There were stellar-sized black holes and there were supermassive black holes. But now there's a lot of different kinds of black holes, which I think is kind of cool, but it's also starting to get a little bit confusing. So let me start by just talking a little bit about the different kinds of black holes. The most common, probably, are stellar-sized black holes. These black holes, well, black holes are generally formed from stars of at least 5 solar masses up to maybe 50 or even higher solar masses. And I'll get to why there's a constraint here. But you need a heavy star to create a black hole. Stars shine by fusion, nuclear fusion. They fuse hydrogen into helium, and then as they get older, they start fusing heavier elements up until the point where they start fusing iron, which requires more energy than it emits. So stars usually stop there. And when they begin to run out of nuclear fuel, the stuff to fuse, because while they're fusing things, there is a pressure that it exerts outward. That's how stars shine. Radiation is going out from the star, from the nuclear fusion. And there's also a gravitational force of the matter that the star is made of pressing down. And most of a star's life is spent in an equilibrium where that radiation pressure is more or less equal to the gravitational pressure pushing it back in. So the star shines for hundreds of millions to several billion years, depending on the type of star it is. But really, really big stars of at least 5 solar masses, when they begin to run out of fuel, that core the radiation pressure starts to lessen. Gravity starts to kick in, and depending on a lot of the details of the star itself, it will either the core will begin to collapse, creating a supernova, which explodes, and then what's left behind is a black hole. It is a giant smashing in of all of the matter in the core to create the black hole. Or it could, because the ranges overlap, and depending on how much of the star actually explodes outward, it could turn into a neutron star. So stars in the range of about 5 to 50 solar masses could either become, depending on the details, a black hole, that's called a core collapse black hole, or a neutron star. Anything less than 5 solar masses isn't enough to create the black hole itself. It doesn't have enough gravitational pressure to squish it in. What ends up happening in those cases is as the core begins to squish in those atoms, then the pressure of the atoms begin to hold it up. In the case of a white dwarf star, it's the electrons of the atoms holding the star up. But if there's even more matter than that, say more than between a sun-sized star and 5 solar masses, it'll even squish down past that, and then the neutrons are holding it up. They're touching each other. It's called neutron degeneracy, and the neutron is holding it up, and you've got a neutron star. But in something bigger, 5+ solar masses, so much pressure is being pushed on that electrons won't hold it up, neutrons won't hold it up, and boom, it goes all the way down into a black hole, into a point that has zero volume, no space whatsoever, and it has infinite density. That's called a singularity. It is a point in space, a point that is mathematically infinite, and I would argue problematic for a lot of theories, especially relativity. But they exist. We know they exist. That is an image of one taken by the Event Horizon Telescope. So black holes do, in fact, really exist. They're not mathematical constructs. So we've got most black holes being created by gravity core collapses, right? And depending on the details of the supernova, if most of the matter goes out into space, what's left behind in the core doesn't get to be as big. Maybe it'll turn into a smaller sized black hole. But this class of black holes, where one star dies and the core collapses, is called a stellar sized black hole, and they have a range of about 5 to 50 solar masses, but anything bigger than that is problematic, and I'll talk about that in just a little bit as I get down this list. So neutron stars are kind of an overlap of the closest kin to a black hole. They are very dense objects. They're only about 10 kilometers across, right? And they have about anywhere from 1.5 to 2 solar masses. The most massive neutron star ever found was 2.1 solar masses. And that's because anything greater than that will collapse into a black hole. Now, remember I said 5 solar masses is the minimum that you need. Well, all of this is a little bit nebulous, to use a pun, and they're working it out. The error bars on this are a little bit bigger. So anywhere from the 2 to 5 solar mass range, I would argue probably either a neutron star or a black hole. So that's one kind of black hole, stellar sized. And then there are supermassive black holes. We've heard of these. Almost every galaxy in the universe has one. And these are black holes that are of the millions of solar masses. Huge. We have one in the center of the Milky Way. It's called Sagittarius A star. 4 million or so solar masses. The one in the center of the Andromeda galaxy is several hundred million solar masses. So these are in the cores of most galaxies, but it's not entirely clear how they form. There's a lot of theories about this. Galaxy formation, especially, is being invoked here a lot. They could be the result. They could be the result of a lot of black hole mergers, which we're starting to observe now with gravitational wave detection. Black holes merge. They come together, doing the black hole dance, and they come together and they make two black holes that are smaller, make a bigger black hole. That could be one way they form. Could be done through galaxy collisions, where several supermassive black holes come together. What's weird, though, is that if it's that way, if it's done by all of these collisions, then why are they being seen so early in the early universe? Astronomers have observed what they think are supermassive black holes up to just a few 100 million years after the Big Bang. So they're present in the early universe, and that is a bit of a conundrum. So there's stellar-sized black holes, and there's supermassive black holes. And finally, there's this other weird kind called intermediate black holes. These are black holes that range in size from about 36,000 to 316,000. I love that range because it's so specific. Solar masses. They're 36,000, 316,000 solar masses. That's the intermediate-sized black holes. And they may exist in the hearts of most dwarf galaxies. And a dwarf galaxy is a very old galaxy. It's very small. We have 2 of them in orbit around the Milky Way. the Large and the Small Magellanic Cloud, and they may have at their centers intermediate-sized black holes, and nobody is sure how many there are. So there's the three main kind that we're used to hearing about, and now let's talk a little bit about the anatomy of a black hole. Now I'm putting this slide up here. Let me do it this way so you guys can see it better. This is an anatomy of a black hole. Remember I said they were relatively simple objects. Well, this is a complicated looking slide, but it's just labeling a lot of the stuff that happened on the outside, mostly, of the black hole itself. You have the singularity. That's it. That's the real black hole right there. And every singularity has an event horizon. That's that spot that once you cross, you die. You don't get to come back from that spot. That's where the force of gravity is so strong, nothing in the known laws of nature can get you back out again. So that's the part that's black. That's the part that you can't return from. Then there's this thing called a photon sphere, which I think is kind of cool. Although the black hole itself is dark, photons are emitted from nearby hot plasma in jets or an accretion disk. And in the absence of gravity, these photons would travel in straight lines. But just outside the event horizon of a black hole, gravity is strong enough to bend their paths so that we see a bright ring surrounding the roughly circular dark shadow. We've seen those in animations where they have that sort of rotating looking little distortion field around them. That's the photon sphere. And then of course black holes have, when things are falling into them, have something called a relativistic jet. And this is the high energy radiation that's given off when matter falls in at relativistic speeds. It's usually high energy gamma radiation and cosmic rays, and it is a very among the brightest objects, if not the brightest object in the universe. When you're looking pole onto one of these jets, when it's pointed right at you, they're the brightest things in the universe. And then you've got this innermost stable orbit and accretion disk. You guys know about that. The accretion disk is just this stuff of material that's coming around. So that's basically your everyday black hole. If it's spinning, which it probably is, then you get that photon sphere that goes all the way around. So so that is the anatomy of a black hole. That's some of the things some of the characteristics that they have. But how many are there? How many black holes in the universe are there? They don't shine. It's hard to see them. The only way to see a black hole is if it's eating something else. And you see those relativistic jets, you got the photon sphere, you got the accretion disk. But if it's not feeding and it's just sitting there, it's black. So how can we figure out how many there are? We need what astronomers call a black hole mass function for the universe. And this is a function of time of how many black holes there are at any given time in the universe. And they're constructing that right now, amazingly enough. So it's estimated that black holes make up 1% of the matter in the universe. And recently some studies had been done, and I've got some links, and I should have put them in the description box, but I didn't have time. Some astronomers have been looking and trying to estimate, in order to get a count for how many black holes there are, tried to find they used a distribution function for stars in the universe to find out how many are paired, how many are binary stars, how many are solo stars, and of those stars, how many are likely to become black holes. And then they made a model, and not only of the lives of the stars, but of the buildup of the life of the star itself, the accreting gas that created the star in the first place. They looked at galaxies as well, their sizes and the sizes of the gas clouds that those galaxies have, and they put all this into their model. And this was a model done just last year, actually. Let's see if I can. I mean, I'll put this up, but Oh, it's gone. I don't have it. It was anyway, I do have a link to it, which I can show you in just a minute, but I don't want to lose track of what I'm saying right now. So once they put their models together, they looked at all the binaries and the solo stars, all the things. They came up with a mass function that estimated that there are 40 quintillion is the word black holes with masses between 5 and 10 times the mass of the sun. Now, that's a lot. That's a lot of them. And these are stellar-sized black holes, and it does not seem to include supermassive black holes. Supermassive black holes, I guess, since it's assumed that almost every galaxy in the universe has one, and there's like how many hundreds of trillions of galaxies in the universe, you get a sense of how many supermassive black holes they are. But of stellar-sized black holes, they're saying 40 quintillion of them. So that's a lot. And they wanted to get as accurate a model as possible based on the mass functions that they have for stars and galaxies in the universe to create this. And they have a function now of time of how many black holes there would be in the universe. And right now, over time, and right now, it's 40 quintillion. Okay, so when I started out, so that's the basics of black holes, right? That's what we've known for a long time, except for maybe the 40 quintillion part, because that was just done last year. But the it doesn't end there. That's the story of black holes gets a little bit stranger as not only with gravitational wave astronomy, but with a lot of the other things that we're learning with the Large Hadron Collider and things like that. So when I did a black hole search of types of black holes, it was you know how Google does a search and then it also gives you related searches of what else people asked for, and it's like, what are the 3 types of black holes? What are the 2 categories of black holes? Well, there was a lot more than I give you 3. There were stellar sized, intermediate sized, and supermassive black holes, but there's more. So we, as I said, stellar size between 5 and 50 or so solar masses, intermediate between 36,000 and 316,000, and supermassive black holes, millions of solar masses. But what the hell is a primordial black hole? And how big are they? That's a new thing. Now, normally you need 5 solar masses, like I said, to make a black hole. For the you need a 5 solar mass star to make a black hole because of the core collapse, right? But there is evidence that they're using gravitational wave astronomy that there may be smaller black holes, anywhere from intermediate sized black holes, which 36,000, all the way down to microscopic black holes. These are black holes that are less than the size of an asteroid, less than the size, in some cases, of an atom, super microscopic, right? And so these would be and by size, we're talking about mass, okay? That's what we generally mean. And the size, the physical size, comes from that. The Schwarzschild radius comes from how massive it is. It's a function of its mass. So they're starting to wonder where did these come from, and it looks like they came from just the few moments after the Big Bang that they would have created. If it's not certain that they exist, there is a lot of a suggestion that these primordial black holes exist, and gravitational wave astronomy is one of those things that's trying to help pin this down. But if they exist, then they were likely formed in the few seconds after the Big Bang. And calculations show that the smallest among them would have evaporated by now, leaving the smallest ones that would be around today, 13 billion years after the Big Bang, would be about the size of an asteroid. Okay, these would be something, 10 to the 20, I forget the number of kilograms they said, but it's basically asteroid mass. That will be the smallest that would still exist today. However, when we look back in the early universe, which JWST is going to be doing a lot of, we can see that the masses were a lot smaller, but they've since evaporated due to Hawking radiation. So, and it's really hard to distinguish these black holes, these asteroid-sized up to planet-sized black holes. It's hard to distinguish them gravitationally from neutron stars. And so the work that's being done on this right now is to try to find a way to differentiate these. That's why everybody that operates a gravitational wave detector, of which there's just one, the LIGO people, they want to see more neutron star mergers, because the telltale signal that they get from that will tell them a lot about the nature of what these neutron stars look like, and can maybe help them differentiate them from these primordial black holes if they exist. But it's hard because of the mass range to tell the difference between the two. So that was pretty cool. But what's even cooler is that if they exist, then astronomers think it could be a source for the dark matter in the universe. It is unknown how many of these primordial black holes would have been created after the Big Bang, but it could have been enough to account for the 25% or so of the matter of the universe that the dark matter is claimed to take right now. So it could be that the primordial black holes are dark matter. That's one theory, one that I find appealing, just because at least there's a story to tell about that. With dark matter, it's just like, well, we know it's there. That's all we know about it. So I think that's pretty cool. And they could also create the dark matter halos that exist around galaxies, all kinds of things like that. So primordial black holes are a pretty new idea, and I did not know much about them until recently. And finally, we have micro black holes. Now, these are a subset of the primordial black holes because they're really, really tiny, but they try to address the question of how can you create a smaller than 5 solar mass black hole. And these are black holes where the quantum mechanical effects play an important role. They're small, they're very tiny, and the ones that were created in the early universe are long gone. They've evaporated by now. But they're generally less than a stellar mass. Like I said, the ones that would be around today, if they exist, will be around the size of an asteroid. And they were likely created, again, like primordial black holes in the early dense environment of the early universe. And what's funny about these is people freaked out about these microscopic black holes when they built the Large Hadron Collider, right? These were these were things that theoretically could be created, but CERN is very clear in their website about this. You know, that these micro black holes are really not possible to create under general relativity without the dense environment of the early universe. But there are some very speculative theories that say that they might be created, that it is possible that they're created. So CERN says that if they were created in the Large Hadron Collider, then they would only last 10 to the minus 27 seconds through decay. They would only last a mere blink of an eye, according to those very same speculative theories. So while the theories allow these microscopic black holes to be created, they don't last very long. Certainly not long enough to start accreting any material and sucking in the Earth or anything like that. It's funny. CERN has, I think, 3 different web pages on this topic. Because remember, there was a lot of fervor about this when they first turned it on. And so microscopic black holes are a theoretical idea. They could exist been created in the early universe. They're almost certainly gone now, the ones that are super tiny. But it would be interesting to see the asteroid-sized ones, the ones that are about the size of a planet or smaller. But again, the difficulty there is telling the difference between them and neutron stars. So it'll be an interesting time going forward. This is why we need gravitational wave observatories. We really got to pin a lot of this stuff down. And it is a golden era for this right now, because this is a brand new set of observation ranges that we can have when we looking at black holes on anything with gravitational effects on it. So it's a really good time, and we need to be able to get more of these observations in. But there is another kind of black hole that I did not know about. And this is actually, I think, been observed by astronomers. And these are black holes that have formed from neutron stars. And the idea is that the intense gravity that's around a neutron star would continuously attract particles around it, mostly of dark matter. Okay, let's say that these are, the microscopic and the primordial black holes are not dark matter. That dark matter is a thing that is separate. So it is possible for these neutron stars to accrete this dark matter onto its surface, so much so that they pass that 5 or so solar mass threshold, and the neutrons that cause the neutron degeneracy, that are holding up the neutron star to begin with, squish, and because they've accreted enough dark matter, and that becomes a black hole. Now, they don't have a name for this, but it's just called black holes that form from neutron stars. But there are some observations, I think, that point to this as one possible explanation. But this is where gravitational astronomy, wave astronomy, is really going to help out, getting more observations into whether that's possible. These black holes should, if they exist, they should follow the same mass distribution throughout the galaxy and universe as neutron stars do. So we can expect to see about as many of them, or at least the amount of them, would be constrained by the mass function of the neutron star. So neutron stars in the universe. And of course, this is best seen in gravitational wave collisions. Again, another reason why astronomers really, really are excited about getting neutron star collisions, or mergers, I should say. So one final question I want to get to, and then I'll stop. And that is, it's an interesting question too. Can a star collapse straight into a black hole without a resulting supernova? Turns out that has been observed, or at least they think there's one such event that they think is attributable to that. So, as we know, most massive stars, they collapse into a core collapse supernova and create a black hole. Massive stars die, the core collapses, boom, off goes a supernova, and then the core continues into a black hole. And this happens to stars that are in between about the 5 to 50 solar mass range, so they think. But now there's a new model out that thinks that maybe the 27 solar mass upper limit might be the upper limit for this. They might think that most core collapse supernovae, these are stars that explode, occur between 5 and 25 or 27 solar masses. Why? Because there was an event, N6946-BH1 was the first star that ever observed turning directly into a black hole. It's 25 solar masses, so it fits with the model they have, and it's 22 million light years away. Astronomers saw a brightening similar to a core collapse supernova, but then it just faded away. No explosion. Study suggests that stars anywhere from 9 or 5 to 9 to 23 to 27 solar masses are the ones with core collapse supernovae, with larger ones going straight to black holes. I thought that was interesting. So it may be that the super large stars, greater than 25 solar masses or so, don't blow up. They just run out of nuclear fuel and boom, go straight into a black hole with no resulting explosion. That would be another, I don't know, it wouldn't be another type of black hole, but it would be a different way of creating a stellar-sized black hole. So that's pretty cool too. And then I will say one more thing. Remember I said that the supermassive black holes that they're seeing in the early universe were a little bit puzzling. How did they get so big so fast? Well, this kind of goes along with this massive star going into a black hole without a supernova idea. One reason we may be seeing I say we, I'm not seeing them. Astronomers are seeing supermassive black holes so early in the universe. We're talking before a billion years after the Big Bang, 500 million, something like that. That's really, really early. The first galaxies have just formed. So if these supermassive black holes are being turned into supermassive black holes by merging with smaller ones and galaxy mergers and things like that, that takes time, right? To do all of that. Can you do it in a half billion years? And it's not clear that it can happen that quickly, but Hubble and others have shown that there are supermassive black holes early in the universe. Well, one idea for this happening is that because the universe was young, it was a lot smaller than it is right now. It was also a lot denser, a lot of very hot gas close together in the universe could have coalesced in such a way that instead of creating a star, if enough 5+ solar mass, or maybe even 50 to 100 solar mass, I don't know how many, but a lot more solar masses worth of gas and dust could have come together to create a much larger intermediate sized black hole almost from the beginning. And some models are suggesting that it's possible to get 1,000,000 or so solar mass worth of gas and stuff from the early universe to come together fast enough. It would have to be fast, because if it was too slow, it would just turn into a star, or a group of stars. And so it would need to come together at relativistic speeds and just overcome the force of radiation pressure that would result by squishing a lot of that gas together and turning it straight into a black hole, a supermassive black hole. So that's one thing. That's one idea, which I think is interesting. It goes similarly to this idea of a star turning into a black hole without blowing up. Um, so something to look for. I mean, that's something I think James Webb will teach us. We will get a lot of observations from the early universe from JWST, and that's going to look at these very first mechanisms, the very first stars that formed, the very first galaxies that formed. And from those observations, I would be amazed if we didn't see some helpful explanation into our models as to whether or not supermassive black holes could have formed that way. So there's my tour. We've toured black holes. And I know there's a lot more to talk about, but I was surprised at just how many different things one can how big the field has gotten. And I attribute a lot of it to the gravitational wave LIGO observations. Okay. Let me just go back and look at some questions. Raj, is there a limit to how big a black hole can become? I don't think so. I mean, we're talking several 100 million solar masses generally for supermassive black holes. Why would there? I don't think there's any interesting or any relativistic reason why we can't just keep. It's all a function of mass, right? It's all a function of how much matter gets past the neutron degeneracy stage and straight into a black hole. You need a lot of mass to do that, and it's all explainable with general relativity. So I don't know. I don't think there is. There's constraints. I mean, on how it can happen in practice. You can't do it without the matter. So if you don't have that much matter falling in, then you're not going to make a very big black hole. Galaxies like IC 1101 elliptical galaxy, the largest galaxy in the universe, is the result of billions of years of galaxy collisions. So it would presumably have among the largest black hole in the universe. If what we think about this is true, that these black holes, supermassive black holes, accrete and collide and merge over time, then that would have among the largest black hole. But that would be the constraint, right? You would have to have these mergers to make a bigger black hole. The early universe would have been compact enough that it probably could have happened in one go. That's why they're thinking they see these supermassive black holes so early. But they're not. I don't recall seeing how massive they were. But to be a supermassive black hole, you've got to be in the million of solar mass range anyway. So, but that would have been a straight to video kind of thing, right? It would have been straight collapse into a black hole. No star, nothing, just straight into it. Otherwise, you've got to wait several 100 million years for these first stars to die in core collapse supernova. So let's see. I'm still anxiously awaiting. This is from Will. I'm waiting the Beetlejuice supernova. Are you? They say it's could happen anytime now. So, yeah. And I think I read in Phil Plate's book, didn't he say that if Beetlejuice explodes, it could affect us in some way? I think the interstellar medium, we could maybe get a buildup, a bow shock of it or something. It's not going to destroy the Earth, but we might get some effect on it. He wrote this book back in the early 2000s about Death from the Sky, it was called, so that you could, have all these disaster scenarios, and supernovae from nearby stars was one of them. Series Lee, let me see if I can understand your comment. The theory is when black holes evaporate and reach the Planck diameter, that then exist forever and are dark matter. Oh, is that what it is? Okay. The Planck diameter, the Planck length is actually the smallest length that can be measured with physics because of the Heisenberg uncertainty principle. We can't know certain things, and this is one of the fundamental limits. The Planck, I think it's 10 to the minus 36 meters. I think I could have it wrong, but it's tiny, very tiny. When black holes evaporate and reach the Planck diameter, then they exist forever and are dark matter. Okay, I hadn't heard that. Jimmy D, no supernova over 27 solar masses sort of takes all the fun out of it. How does it do that? It's just like you want to see these like hypernova and all. I mean, I don't know at what point the hypernova take over. How big are some of these stars? VY Canis Majoris is one that popped. I did a video on that. I have to remind myself about the numbers, but yeah, they're putting a kind of an upper limit on this. As stars larger than that just go straight to a black hole. Raj is commenting, black holes grow by consuming mass. I think if there's no mass to consume, the black hole will evaporate. Yeah, I don't want to get into that too much because that's just a whole nother thing. But black holes evaporate via something called Hawking radiation. And it's this idea, as I understand it, off the top of my head, that near the event horizon, with the point at which things either fall in and can't escape or they can escape, there are these, space-time has this virtual vacuum where particles and antiparticles are created spontaneously. They immediately annihilate each other. So it's just called this vacuum energy. And it is in some ways, and Sean Carroll, I think, actually proposed that this might be one of the things that contribute to dark energy. But anyway, near the event horizon, these particle-antiparticle pairs are created, and one of them goes in the black hole, one of them doesn't, and that somehow has the effect. That's the radiation part. That's how black holes can radiate. But how they then evaporate and lose mass is a little bit lost to me. I can't tell you that. I don't know how they end up with zero mass. But, I'm not going to say, Stephen Hawking knew his business. So it was somehow they get to be non-existent. It takes a really, really long time. The last objects, the heat death of the universe, among the last objects that happened trillions and trillions of years of now, the only things that will be left long after red dwarf stars have died will be black holes, and then they will evaporate, and then there's nothing. Now, we didn't actually have a black hole Planck length Planck-sized remnant black hole. I just talked about microscopic black holes in a very, high level. I didn't get into Planck length or Planck's, Planck size and all that. So we didn't talk about it because I'm trying to talk about all these other things in one hangout. So Dan from Canada, I can't wrap my head around why we cannot detect black holes by they would show a hole in the background radiation as they do not allow infrared radiation out. They show no temperature compared to space around them. Am I out of my mind? Well, you maybe, but not for that question. You're thinking about the cosmic microwave background. While in one sense you can think of it as a backdrop of radiation against which you might be able to see shadows, but that's not how it works. The cosmic microwave background is the remnant of the Big Bang at a point. It was when it's a fingerprint or a footprint of what was left over from the Big Bang when it reionized. I'm sorry, when the universe became transparent, and what's left is that imprint. Now, when it happened, it was very hot and very dense. But over time, over the course of the age of the universe, that radiation has cooled, and it's basically in the microwave region of the spectrum. But it is a distinct thing that you look at when you look at it. You are looking effectively at this point in history of the universe. A current black hole that might be sitting between us and that isn't going to cast a shadow on it. So you're not going to see like the imprint of a black hole against it. But you are correct when you say that the only way we can see a black hole is its effects on things around it. So if by some miracle there was a very bright emission nebula, some 50 light years away, and a stellar-sized black hole was traversing between us and it, then if all the conditions are right, we might see the effect of that black hole against that nebula. But I think the arrangement of that would have to be pretty fortuitous to make that happen. But to compare it to the cosmic microwave background you can't do that. So that's my response to your question. But it is a good idea. But the only way we can observe these things directly is by looking at it feeding on something else, by pulling in material. Ideally, that's the way we see them, and the radiation being the radiation of the particles being accelerated that's given off. That's what we see. And that's the only way we can see it. These relativistic jets that pop up, all of that is the effects of a black hole on its surroundings. So in any scenario you can think of where that happens, then we can see the black hole. But most of space is pretty darn empty. And stellar-sized black holes are just sitting there not eating on stuff. And the interstellar medium and the intergalactic medium isn't dense enough to really show any kind of radiation signature from it. So the only way we're going to see a black hole that isn't eating is if it collides with another one and distorts the fabric of space-time in a way that we can see it with our detectors and gravitational waves. So they're hard to see. They're black. Bullshit vendor. Let's see if I can understand your question. Won't a black hole pop back up when it's evaporated off? Mass energy beyond what went into it when it collapsed. Won't a black hole pop back up when it's evaporated off? Mass and energy beyond what went into. I'm sorry, I don't understand that question. I don't think I can imagine a black hole popping back up when it's evaporated. Yeah, I'm sorry, I don't understand the question. Try it again. Write it in a different way, maybe. Nick wants to know, I wonder if the universe is cyclic and macroscopic black holes are remnants of the end of the last epoch of black holes in some way. Yeah. I mean, there's no way to really answer that, is there? Plenty of theories about that. We're one of many universes, one of multiverses. We're parallel infinite number of universes going alongside us. We are a bubble universe that started. Maybe we're seeing black holes from other bubbles. Yeah, I mean, these are all things to say, but I don't know how to prove any of them. Some physicists believe that the RHIC and the LHC have created them, and many Planck-sized remnants. Okay, I don't know about that. If the universe was extremely dense at the beginning, why didn't the universe just collapse into black holes? Yeah, that's a good question. I think it all depends on the exact distribution of matter in the universe, doesn't it? And I mean, why do we have the amount of matter we have now? A lot of it was annihilated in the Big Bang, but some of it was a small imbalance. Everything that we see in our universe right now is a result of just a tiny imbalance of matter antimatter, and matter won out, and we have what we have now. And it dispersed the way it did. And let's say that the early universe was dense enough so that several million solar masses worth of gas and dust came together, mostly gas because dust wouldn't have been around much then, came together to form black holes. A lot would depend on the exact distribution of that gas, right? And the tendrils, the cosmic web that we've come to call it, of where the galaxies ended up forming. Obviously, it wasn't enough where black holes just kept forming and forming and forming until finally we had nothing but black holes that collided with each other and then sucked in, and all we have is one big black hole. That obviously didn't happen. So why it didn't happen, I think, is the devil's in the details. It's in the exact distribution of the matter in the early universe because of the nature of the Big Bang itself. What won out, the dark matter distribution or black hole distribution that sculpted the cosmic web, the pattern that we see in all of the galaxies on the large scale structure of the universe came from those initial conditions. And obviously, it wasn't uniform. So there must have been enough irregularities and homogeneities to create stars, galaxies, and black holes. And of course, as the universe kept expanding, it became harder and harder for those black holes to come together. But this is all stuff we need to learn. And I think JWST is going to be the big winner in teaching us a lot of this stuff. Let's see. The Soul Soprano. Did black holes make mass, or did mass create black holes? If large amounts of energy crush down to make a SR, it's a bit like chicken and egg question. Did black holes make mass, or did mass make? I think it's the mass created the black holes part. Black holes come from general relativity. They're a prediction of that, and as we know, relativity is a study of gravitational interaction between mass, energy, and space-time. And so, I think I don't think you start with black holes and somehow get mass. I think you need to start with mass and get black holes. I hope. I don't know what SR is. So, from Raj, I wonder if a black hole is an accurate name for them. And with the confirmation of the existence of a black hole, would this mean a white hole exists? Yeah, I mean, I don't know. Black holes were predicted by relativity. I don't know if white holes were. Given that I've said many times, black holes are a problem for relativity. You don't want your theory to have singularities in it. That's something that needs to be worked out. What that means is that the event horizon marks a place beyond which the theory no longer works. So what do we do with that area past the event horizon? We need something else. We need an extension of general relativity that doesn't include singularities in it. And that's, I think, where a lot of work is being put right now. But black holes are a problem. I mean, that, the fact that they exist is, I don't think, in question anymore. But there must be something more about them. The idea that we can never know what's going on past the event horizon is a problem. And so, does that follow that there's a white hole? I don't see that it follows. I think that it's a point that needs to be better described mathematically than just saying it's an infinite density. Scott Morrison. Okay, real question. Oh, good, because I hate the fake ones. It seems to me when a black dot hole is created, it causes a big bang on the other end, creating a new universe. Wouldn't that explain how the universe was created from nothing? Except that the universe wasn't created from nothing. In that scenario, it would be created from the contents of a black hole. But going back to what I just said, everybody's really wanting to know what's going on down at this singularity. And right now it's unknowable. Is this possible, what you're suggesting, creating an entire universe? I think you need to invoke a lot of things I don't understand to make that happen. And we start getting into things like multiverses and quantum mechanics and things like that, and I start getting irritated. So I can't really talk about that. I'm not qualified to say anything really about it, but maybe is I guess all I can say. Are black holes and dark matter / energy in some way linked, given that there is so little matter as we know it? Well, yes, black holes and dark matter, not so much dark energy. Okay. Dark matter and dark energy are not really related to one another. They just happen to have the term dark in it. But they are saying, and I've said this in this little presentation here, that black holes, especially these microscopic ones or these primordial black holes, could be the dark matter that we think that we're talking about. They're not really sure primordial black holes exist, but if they did, then it could explain dark matter. Not dark energy. That is the expansion of the universe. The force that is associated, the energy associated with the force that is causing an acceleration of space-time in the universe. And that is not related to dark matter. It will affect it. I mean, the expansion rate of the universe is probably affected by dark matter, but not in any other real way. So, Stephen Porter. Why are all planets, stars, and black holes spheres if dark matter is stretching out the universe and stronger than gravity? I don't know. Stephen. Am I in George Jetson's house? Yes. Doon, 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 doon. Like my background. This was a wallpaper from Pop OS. I'm using the Pop OS distro for Linux, and I found these in there, and I'm like, oh, I love these backgrounds, and so I stole it. That's what that is. Let's see. I've read a theory that black hole formation can trigger star formation. Yeah, lots of things can trigger star formation, actually. Galaxies colliding. It turns out that when two galaxies collide, there's, their gases intermingle. You see a burst of star formation happening during that time. You also see a lot of supernovae going on during galaxy collisions for, I think, the same reason. And so they're, at least if one doesn't cause the other, they're certainly happening at similar times when galaxies collide. So that's kind of cool. Dennis is asking, could black holes have formed in the early universe without becoming a sun first, just due to the high concentration of matter? Yeah, that's what I was talking about, right? So yes, the answer to your question is that could, and that's what they're looking at with a lot of these as an explanation for how supermassive black holes could have formed so soon after the Big Bang. So yes, the answer to your question, absolutely. You probably asked that before I got to that part of my little spiel. So, but yeah, that's a good question, Dennis. You're on top of it, man. Um, let's see. Galaxia, hi there. The black holes 300,000 years after the Big Bang are too much the same temperature as their environment to pop up in the background radiation. Yes, that's right. If there are black holes, I see. Maybe I misunderstood Dan's question. Would those black holes of the same epoch of the universe be visible against the background radiation? If that's your question and I misunderstood it and I apologize, I thought we were comparing epochs here, and you can't. Then Galaxy is right, that these temperatures are very similar, uh, depending, I think, on how much after the Big Bang those black holes will have formed. But but yes, that is a good statement, Galaxy. I agree with that. Jimmy D, could JWST teach the formation of new galaxies formation of a supermassive black hole? Yes. It's going to look at those very first galaxies, right? It's going to look at the very first stars and galaxies. So it should see, it was going to help a lot, I think, with our understanding of galaxy models. So James Webb is going to turn space into a Christmas tree. Yes, it will. And Ceres is right about this. The Big Bang is not an explosion of matter and energy. It was an explosion of space-time itself. The time, gravity, too hot and unite. The time, gravity, too hot and unite with other forced and make repulsive. But you're right. I understand the first part. It was not an explosion in time. It was an explosion of time. So everything was created at once. And I promised that I would do this. Let me go see if anybody's sitting in. Where's my. Where my Discord went. Oh, there it is. Let's see. Tony's in there. Let me go see. Let me join real quick. Hey, Tony, you there? Anyway, if you want to say anything, go for it. Otherwise, I'll just keep going. You're not live, by the way. So if you start talking, I'll make you live. Okay. And especially when it recreates the Hubble Deep Field and Ultra Deep Field, those two patches of space is going to look like Dayglow nightclub. That's true, man. Those are going to be impressive images. They really are. The very first deep fields that Hubble or that JWST takes. I can't wait. And I've said this before in past streams about JWST. I don't care about the pretty pictures of JWST. It'll make some. But I'm more interested in the ones that are just little faint fuzzy blobs, because those will be the most valuable images as far as the context of our universe is. I mean, we're going to be looking at I want to see the image of the very first star that ever shone. That would be impressive. I want to see, and it's going to be just a dot, but it's the context. Oh, there you are. Okay. Did you want to say anything? Hello?
I think you covered things. I actually came in a little bit late, but
Okay.
I was just listening, and
All right.
I like that you have this thing, but I don't really have anything to
Okay.
contribute
That's
at this
fine. It's
time.
just one more way to chat. So if you don't got anything to say, it's no problem. But if anybody does, you could join. I'm going to head out here pretty soon. So I've never used Discord, but thinking of signing up to check out Deep Astronomy. Yes, man. That's where our cult lives. We all clicked on the same links. In fact, Peter provides us with all of our links that we click on. So we go and we click on the same links and we become algorithmically joined. We huddle in our little algorithm together. We are algorithm buddies. And so we all click on the same thing, and we all And he just posted an article from Ethan Siegel, one of my favorite guys. Are we living in a baby universe that looks like a black hole to outsiders? And if you don't follow Ethan Siegel, then you should listen to his podcast, read his articles. He starts with a bang is his Twitter handle. Probably the best science communicator I know besides Sean Carroll. So I'd highly recommend his stuff. But anyway, yeah, join Discord, man, and we can chat and do. I'm thinking of doing things only on Discord in the future. I'm not sure what, but if enough people want to get together and do stuff, we'll probably do it on Discord. It's way better than some of these other channels. So I'm thinking about it. Joseph Eck, if our universe is black hole in some higher space and do evaporate in this higher space, how does this evaporation look like from our perspective inside? Could evaporation from outside be expanding from inside? Evaporation from outside be oh, I see. So are you talking about I think if I understand what you're saying, then this virtual energy I was talking about, this vacuum energy that I was talking about, these spontaneous particle-antiparticle creation and annihilation that's happening in the fabric of space-time, could that be evaporation from another bubble? Yeah, I mean, some higher space. Well, the problem with all of this, and this is why I don't like quantum mechanics, I don't like talking about it, I definitely don't like talking about the multiverse, is that there's nothing we could do about it. It's just words. We could say other universe, we could say out what did you call it? A higher space, but we can't interact with it in any real way, although you're suggesting that we could by this evaporation coming from them to us. But my understanding of all of these universes and all of these higher spaces is that they cannot interact. They simply cannot. Physics will not allow. Our physics is different from the physics somewhere else. And so those two things do not mix. It's kind of like dividing by zero. you just can't do it. You can try to do it, which we do here often, but I don't know. I just don't know what to say about that. It's just nothing we can ever do to find that out, and to me that's like a problem. Yeah, and Nick is commenting, there's a lot of theoretical minds here, me included. I know. Theories are great. They are, and we don't get forward without them. But unprovable or untestable theories are just a conversation. It's a sort of rumination on what be. It's science fiction. It's nothing we can practically deal with here in this universe. I'm talking about these quantum mechanical ideas, these many worlds interpretations and all this kind of stuff, right? Yes, quantum mechanics is becoming more useful than it ever has in the past. We're starting to measure entanglement. We're starting to build quantum computers and use the principles on which quantum mechanics is built in the universe to actually use it. So it is becoming more and more practical. But there's some parts of it that by definition will never be practical, and that's one of them. And so talking about it is fun, but that's all it is. It's never going to be anything more than just fun. It's not like the Higgs boson, right? Remember, he was given a lot of grief that the Higgs boson is never going to be detectable. It's predicted by a theory, but we're never going to be able to detect it, yada yada. Well, that was detected. That was just a technology issue, right? We couldn't at the time, but technology got better and we were able to find. This isn't like that with many worlds. It doesn't matter the technological level that we get to. Physics simply says we can't interact in much the same way as physics says we can't interact with beyond the event horizon. So if that's true, we need more physics, right? Black holes exist. We know that. We've seen them. We've detected them. We know they're there. General relativity is right up to a point. But beyond there is a point at which it does not work. And we need something that does work to interact with the other side of an event horizon of a black hole in any meaningful way. Is that possible? Perhaps. But built into many worlds is the idea that you can never do this. So I have a problem with that. I'm not saying that we're not going to be able to get into, understand what's going on the other side of an event horizon. But there is nature built into the theory, the idea that you can't ever interact or know what's going on with these infinite number of universes that are out there. So I don't know. Hey, CD, it's good to see you. Where are you? Are you on Twitch? Yeah, it looks like it. So it's good to see you, man. I'm glad you're here. I'm getting ready to close down, though. I mean, we are losing matter and energy from our cosmic horizon. Are we losing it, or is it just becoming out of our reach? And the universe is expanding, and some things are expanding away from us to the point where no matter what we do, we can never reach them again. That's not the same thing as losing it entirely. It's still there. It's just our physics is limiting us to get there, to seeing it. So we are losing that matter and energy forever just by the expansion of the universe. And that just means no matter how fast we travel, even at the speed of light, we're never going to catch up to these things that have already been expanding for 13 billion years. But it hasn't actually been lost. It's just not in the observable universe. So that's a little bit different than saying we've lost it entirely in the universe. And I know that's what you mean. But the cosmic horizon, I think, is what, you're talking about, the observable universe. Okay. I think I've answered or shown most of the comments. Let me just show this one. Soul Soprano is commenting. That will be fantastic, James. I hope it covers the same patch of space to give a deeper infrared image of it. Are you talking? You're talking about maybe looking at one of the other deep fields that Hubble looked at. I don't know if they'll waste time on that. They might. They might.
Yeah, I would really like to see James Webb do the exact same space, because it just gets deeper, right? So we
Yeah, but which one?
That's
Which one though? Because it's done like 10 deep fields. There's the original, there's the ultra, there's the extreme. So which one? I mean, then there's all the frontier fields too. There was 6 of those. So how many? I mean, which one? I think I'd like to see the very first one, right? The one that was done in Ursa Major, the very first one that was done in '95. Go
yeah,
back
but
and look.
we got 20 years for the James Webb at current. So I mean,
Well,
we've got
actually,
time.
yeah, that's true nominally, and because we were talking about this last week, because ESA did such a good job with the launch, maybe up to 20 years of at least fuel available for James Webb. So, yeah. Now the question is, can the detectors last, and all the other accoutrements that go with a space telescope? But the fuel's there, and that was the limiting factor before. Yeah, so there's hey Christian. So yeah, there's the deep field, then there's the ultra deep field, and then there's the extreme deep field, which I think was done in 2009, and then there was the frontier fields, which were done in like 2015, 2014. There were 6 of those, and but yeah, the deep field and the ultra deep field were the 2 biggies. First of them saw about 3,000 to 5,000 galaxies in the deep field. They did it again in, I think it's Fornax, the constellation Fornax, found 10,000 galaxies. And then I forget where the extreme deep field looked, but yeah. Oh, okay. I didn't know that. So the extreme was the ultra deep field, but done with C3. Okay. They had replaced the camera and did it again. So, before it was done with the wide field planet, what's it called? The wide field planetary camera 2 or some WIFPIC wide field planetary camera 2. Yeah. That was what did the deep field and the ultra deep field. So, Galaxy. There's only one ultra deep field. The others aren't really fully new deep fields, let alone if they were ultra. Okay, but I gotta say the frontier fields were important, and they were, I think, as long exposure time as the ultra deep field. I can't remember. I have to look it up. But what the Frontier Fields project did was it took what they call parallel fields. It looked at a galaxy cluster. They picked 6 of them, and they were doing lensing of these galaxy clusters to see very, very distant things that Hubble wouldn't ordinarily be powerful enough to see. It used galaxy clusters as a lens to collect more light and to focus more light from even more distant galaxies onto Hubble's detectors than it would have been able to do otherwise. And at the same time, while it was doing that, it was looking at a field, a patch of sky right next to that galaxy cluster because they could. It was pointing there. They just went ahead and imaged it as well. And the idea behind it was to see if there were Hubble deep fields were more or less isotropic. In other words, were they more or less the same everywhere it looked? Were these galaxies, because when they filled the image, when those galaxies filled the image, it was all more or less the same, right? There was just a smattering of galaxies. All of them kind of filled the image. But was it the same in another part of the sky? Or was it only right there? And so that's what they were trying to figure out with those deep fields, and they discovered that it's pretty much the same. Everywhere you look, you're going to fill your detector with these deep fields, with galaxies, and that's just amazing, right? And then, of course, they revised all of the counts for galaxies. We went from 100 billion galaxies to, I don't know what it was, some trillions of numbers. You get these numbers that are so big after a while, they don't mean nothing to me. So I just big, lots, right? But it was more or less the same everywhere it looked, and that's one of the things that Frontier Fields wanted to find out, because people can't get enough of these deep fields, and I'm one of them. So it pointing JWST at something like that, any of those would be fine. But still, I want to see the first galaxy, or at least one of the first galaxies, and I want to see the first star. It's not going to be remarkable. The galaxies back then were weird, misshapen. They didn't have any real contours to them. They just kind of blobs, right? They're just blobby. You can see that in the deep fields. You can see they don't look like beautiful spirals or any of that stuff. They're just blobs. And these early galaxies aren't much to look at, but that's what I want to see. Those photons will have traveled from just a few hundred or few million to a few 100 million years after the Big Bang, and spent their entire history of the universe getting to the detectors on the James Webb Space Telescope. And that means something. That's some context right there. And that's what I want to see. That's what I'm most excited about seeing from JWST. That and the first spectra of an exoplanet's atmosphere that has biosignatures in it. That I also want to see. Now they're going to be looking at TRAPPIST-1. We've already talked about that. TRAPPIST-1D, I think. But it's going to be looking at other exoplanets the first year of observations, but that'll be the big one. And I want to see that too. I want to see I want to see any atmospheric spectra, but I would be very interested in seeing one that had biosignatures in it. The more that have spectra of atmospheres, that's an important piece of information, because right now we're saying when we discover an exoplanet and we confirm it, so TESS looks at a spot in the sky and it makes a candidate. The candidates it becomes an object of interest. And then as it becomes an object of interest, other observatories go and they look at it to make it a verified exoplanet, which, by the way, there are now 5,000 candidates, I think, from TESS, over 5,000 candidates from TESS objects of interest that it's looking at. Of those, and those that Kepler had found, how many have atmospheres? I'd love to know that, right? If we're starting to see atmospheres in a lot of these things from JWST, that's a huge data point, that how common atmospheres are. Right now, they're saying that it could have an atmosphere. We've discovered a rocky or super Earth, and it could have an atmosphere. And if it does have an atmosphere, it's probably made of this. And it might be, if it has water, because it's in the habitable zone, it might be a water world. They're just making all this up. They're just saying stuff because all they really know is that A, the planet is there, B, that it's orbiting its star at a certain distance that could have liquid water if it had any liquid water. And that's about it. There's not a whole lot else they're knowing about this thing. They could do some radial velocity measurements and get the mass, but that's it. JWST is going to look at it directly. It's going to block out the light from that star, look at that exoplanet, and it's going to open up near spec, and it's going to look at the spectra of that planet as the light travels through the atmosphere, and it's going to show us what it's made of. That is cool. All right. But that's not black holes. Why are we talking? We're not talking about black holes anymore. Now we're talking about, well, that's because I went off and I decided what I wanted. What I wanted to see. All right, guys, I am going to head out. I got to go. See you next week and Tuesday. And I don't know yet what. Oh, please listen to Space Junk Podcast. I posted it yesterday. New format. You're going to recognize the topic because I talked about terraforming the moon. But I changed the format of the episodes now. So now there's 20 minutes of a topic that I think anybody would be interested in, whether you care about telescopes or not. And then there's the part with telescopes and gear. And then there's the part where I talk about some space news. So let me know what you think of this new format. Go listen to a Space Junk Podcast. It's on all the things. I upload it to Anchor and it sends it off to Spotify and iTunes and everybody. I even when Hans Milling asked me to put it on his thing for his car that he has on here, I got it on that. So if you're not seeing Space Junk Podcast, let me know and I will put it on the thing that you're using to listen to podcasts. I will do that for you because I care about you and I really am excited about this podcast format. So I hope you guys like it. So please check it out. Okay, guys, thank you for joining me. Thank you for clicking on the same links I do so that we all are together and I know about you. If we didn't click on all the same links, then the algorithms wouldn't bring us together and we are all kindred spirits in the link.
Thank you, Tony.
No, you're welcome, Tony. All right. Take it easy. Thank you all so much for watching / listening. And as always, keep
looking up.
Oh, do that again. That was cool. Do it again.
Keep looking up.
Up. There you go. That's right. Thank you, Tony. All right.